Hi, hope you all are having fun learning industrial robots through implementation. In my last lecture, I discussed how an industrial robot is installed and it is put to use. After the installation, I showed you how a robot can move at its joint level by simple jogging. Okay, so in the today's lecture, I'll be discussing some more preliminary tasks that are mandatory to put the robot to use to its full capacity. Okay, so let us start today's class. So let me first introduce you to the complete problem, what it is and why is it so important. Just watch this video carefully, how an industrial robot is constructed inside, how there are multiple transmissions which are there. So just watch carefully. Okay, so you see this is a simple actuators which are at the rear part of the link. You will find you have actuators. There are actuators at many other places too. So this is an actuator with its end cover removed. Okay. So now let me run this video. So you see how they are constructed and how they are interconnected. Okay. So these are the transmission which is there. So that moves. There are gear boxes which are inside. There are belt. There are pulley drives. So it has started moving with the gearbox open now. So axis 4 is moving. Now you can understand. See, axis 4 is moving. Now axis 5 is getting moved, and I have just put a marker so that you can understand the movement of the belt. It is a twisted belt. It is not a straight connected belt, and that is driving the pulley. It is a timing belt so that it doesn't slip. There are multiple concentric shafts which are there, which is driving multiple pulleys together. Some idling pulleys are also there. This is axis 5. Now the internal pulley is inside. The pulley that is inside is now getting moved. So I have put another marker inside so that you can understand that as well. So yes, that is driving axis 6. Got it? So axis 5, axis 6, axis 4 was moving. That was directly coupled from the outermost part of the concentric shaft. Okay, now let me see from its rear part. Okay, when all the end covers are open, and these are 3 actuators which are there with the end fitted with resolvers. So you see they are now open. One by one I am moving axis 4, 5 and 6. So they are moved. Okay. So there is some coupling. There are some transmission which are there which connects the motor to the encoder on the one side of it and motor to the transmission system and finally to the link on the other side of it. So you got it. It is quite complicated inside. Okay, at least for axis 4, 5 and 6 where it has multiple transmissions which are there inside. Okay. So multiple joints are getting moved. So you see there are 2 which are moving simultaneously now. What you can see now is this joint which is there, axis 1 which is there. There is a marker, you see. I have magnified it here. So that marker actually says the exact 0 location of the axis. If you say my joint angle is 0 degree at axis number 1, so where is that? With respect to what it is getting measured? So it is with respect to the base which is fixed to the ground, okay, at least for axis 1. Okay, if the later links are to be understood, so it is always with respect to the previous link. Okay, so that is a standard marker which is there normally in all the industrial robots so that you can exactly understand whether it is exactly at 0 or it is not. Okay, so the problem here it says, which is known as a mastering commonly. Okay, the mechanical position and the electrical position of the robot's joints are aligned. What does it mean? When you say it is at 0 degree, mechanical 0 degree, electronic encoders which are fitted at the end, that also should say yes, it is at 0 degrees, so that you can get a correct feedback and your kinematics is well understood by the controller. So if you command it to go to a particular position, let's say XYZ, and you calculate theta is equal to 126, whatever angle you have calculated using inverse kinematics or any other algorithm. So you have understood, okay, I have to go to theta 1 to theta 6 for all the angles. Now your controller should create a closed loop using the feedback that is coming. So you got the complete picture now. So in order to go to any joint angle, joint itself should give you a correct feedback, and that is given by electronic encoders. Okay, so that is what is electronic zeroing that we can say. Okay, so that encoder should also give you an 0 degree. Got it? So that is what is a process of mastering. So when you attach an encoder at the end of a robot, it is not necessary that it is always matched with the mechanical zero axis. It can be little offset in terms of angles. Okay, so in that case, you have to just understand, yes, this much is my offset, and if I say 0, I'll start from, let's say, 10. Okay, so if it is 10, it is 20. If it is 20, it is 30. So that is how that offset will continuously remain there. So that offset is to be understood well, and same in both clockwise and counterclockwise directions. So that is what is mastering, when both the mechanical position and the electronic position of the robot joints are aligned. Okay, so this is the encoder which is fitted at the rear part of your actuator. So this is the actuator. The process involves moving the robot to a predefined mechanical position, that is the 0 position, that is commonly known as the mastering position, or sometimes as home position also, and save the encoder values for that. So this is the offset that you are going to save. So if you are at 0, your encoder says something, and that is what is to be stored. So that is the first thing that we are going to do. Okay, and mastering is required at least when you have first installed your robot. Okay, because it has come through long transportation maybe. In that case, it might have hit somewhere, and whatever manufacturer might have set this 0 position, it must have further turned, or maybe there is some gear shift, maybe some error that has happened. So you have to recalibrate that particular offset. Okay, so during the first run it is mandatory, and robot sometimes their controller has an interlock, so that you cannot move ahead without first time mastering your system. Okay, so this is the first time that you do it. And after maintenance, you see, if you have removed the motor, that also will remove the encoder. The transmission, you are engaged in some gearbox condition, and next time you engage it in a different way, so that offset is also generated. Your belt, if you have taken it out, that connects the input and the output shaft, so once you put it back, there must be some offset between the input and output. When you open it and when you put it back, they are not the same. Okay, so while overhauling any transmission system, while overhauling the motor, while overhauling the gearbox, or maybe encoder, or any part of the system that can affect the feedback, you have to do mastering. Okay, so this picture shows a typical maintenance which is carried out in the robot encoder, and sometimes in the gearbox, and some other, the whole of the motor is getting removed, you see. So this kind of maintenance which are normally done if the robot has surpassed some definite amount of running hours. So planned maintenance also you do it sometimes after the breakdown. So yes, robot can move without the controller. Okay, your controller has arrived in a different package, and your robot has come in a different package. Okay, and your robot can move without the controller actually commanded the robot to move, and that doesn't know that robot has already moved. Okay, so that feedback is lost. Okay, whatever the value that the manufacturer might have configured while first run of this controller and the robot pair, okay, that is lost. Okay, So your robot should not move without the controller. Sometimes it can be moved for maintenance purpose using some special release arrangement which are there in some robots. Okay, if that release mechanism is used and robot moves without the controller, then also you need to do this. Okay, and after an impact with a physical joint stops. So your each and every joint, I'll show you the picture first. So this is these are the physical stops which are there. So that is there in this robot, in my toy robot, that is the demo robot also, that is there, you see, it is here. So that hits this body. So if it comes like this very hard, okay, while moving it hits like this very hard. Okay, in that case also it is quite possible that it has lost its mastering. Okay, so this is the physical stop, you see, after a big collision maybe. So I'll show you another video which shows collision. This is a coordinated motion between the tool and the system. You see, the robot was programmed in some way and it found the system in some other way. So these are some of the instances which are very, very common in the industry. It should not happen, but if it does happen, you have to take care and you have to remaster your robot. Okay. So in case of regular stops, at least when you handle your robot in a standard way using emergency stop, if you stop it, using dedicated stop button if you are doing it, switching off the drives. So in those cases, your mastering is preserved by the controller. Okay, so controller continuously get the feedback, it even gets the feedback, yes, now my emergency stop is pressed and I have to save the values which are there. Okay, so while the motor moves, your feedback continuously changes. So hope you understand that. So okay, so this is what is mastering and that is the problem and you have to deal with it. It is very, very simple to understand the problem. Once it is understood well, there are a number of ways to do it. Okay, there are few standard ways as well, so we'll discuss that. So some of the important notes that I'll make it here. A mastered robot can be programmed to move to any positions quite accurately. Over the period of time, there may be some gear backlash that has happened. Your belt might have become little loose and you can tighten it, and then in those cases it loses its precision. So you have to recalibrate your robot, you have to remaster your system so that it keeps on working to a very good accuracy. Okay, so maintain the accuracy of your robot. It is very much required after certain amount of time. Okay, a mastered robot can be moved to the Cartesian coordinates, because you know inverse kinematics is going to give you angles. If at all you have commanded to go to x, y and z, you have calculated theta 1 to theta 6. So you have to command for this, and this cannot be achieved without a continuous feedback from your encoders. That is the angle feedback device. Okay, so that feedback should be matched with the mechanical angles which are to be commanded. So that continuous servo can be done. Okay, even two identical robots, you know, which has the same type of encoders fitted, the counts can vary for the same pose. Okay, so you have to recalibrate. Even you cannot save the value from one of the robot to the other robot. Okay, so it is mandatory even for a twin robot, which are there in the industry quite commonly. Okay, ambient condition must be maintained during complete procedure of mastering. Now you understand why, because your arms, your transmission system, there are some dimensional changes if at all temperature is changed. Okay, if temperature has changed, that dimensional change can cause some relative change in the angles or the displacement which are there. And in order to accurately match it with the whole of the system, so you have to take care that ambient condition, at least the temperature should be maintained throughout the calibration procedure. Okay, So mastering external axis. Sometimes your robot also has got an external axis like a turntable. It is there. Okay. So in that case, that turntable is also controlled by the robot controller. So that becomes the seventh axis. So that also needs to be mastered. You should know the zero and you should understand there is some kinematic linkage between the robot and the external axis as well, so that it can be work together. Okay, so that is the reason mastering is also required for any external axis if it is there. Okay, mastering data vary with the loaded and unloaded robot. Okay, so if at all your robot is loaded with, let's say, 200 kg over here, that must have caused some sort of angular changes due to the amount of torsion that is coming to the shaft, gear shaft, okay, and to the belts, to all the transmission that is there between the robot and the end effector. So that has caused some shift. Okay, so that also needs to be recorded. Okay, so that when you master with a bare robot without the load, it can perform well. But when you have loaded it, there must be some kind of flexibility which is there. It is not very sturdy enough to hold that load sometimes. Okay, so a little bit of lack of stiffness is there sometimes. So those are also to be recorded. So in order to do that, you have to put the robot with a dedicated load which is for which it is designed, or the load with which you want to work with. Okay, you have to put that load here and then master it. So you need to know the offset. Your controller needs to know the offset with the loaded robot and unloaded robot. Got it? So if your robot is going to carry multiple loads during its job, so you have to calibrate your robot for all the different loads that it is going to carry. Okay, so sometimes it is very, very important if it is a very, very precise task which is to be performed by the robot. Okay, so now there are many mastering methods which are there. Few of them are listed here. First four will be doing. This is with the loaded and unloaded that I have just told. Okay, so that is there. The rest four methods I'll discuss now. Okay, so this is the clear picture of all the axes with their zero position shown by relative zero position marked over here between the third link and the fourth one, 0 and 1, 1 and 2, 2 and 3, 3 and 4, 4 and 5, 5 and 6. So you got its angle markers are there, you can see. Okay, and your joints also has encoders which are here for all the axes 1 to 6 of Yaskawa GP12 arm. So this is not very necessary to see this exact location and all. Only seeing this is helpful, at least for manual mastering. Okay, so this is just for your knowledge. These are the actuators which are fitted with encoders at the end. Okay, these are not quite visible here, whereas this is very, very clearly written encoder. So these are for axis 5 and 6. Those are small motors which are there. Okay, so yes, Yaskawa GP12 robot, it allows doing mastering using teach pendant, manual mastering using teach pendant. So you just using this menu driven system, GUI or HMI you can call it, or teach pendant is there. So you select the robot, you select the homing for the position you want to do. So it quickly shows all the joint encoder data over here. So what you have to do, you have to manually make all the axes aligned to 0, 0 position for all the axes, and you can simultaneously master them all. You can select them all over here, all the check boxes. Okay, you can save all the encoder values which are there for the given 0, 0, 0, 0, 0 position for all the joints. So the controller saves it, and then it is ready to record the joint angles. Actually it records, it gives the encoder gives you the encoder count, and then it is further converted to the joint angles. That is shown as roll, pitch, yaw, whatever joint angles and all. So that is shown after converting the encoder to the joint angle positions. Okay, so this is quite trivial, quite easy to understand. You just take the robot to 0 and record the whatever is the joint encoder values and you are done. So that is a manual calibration or mastering. So there is another very good way of doing it, KUKA industrial robot, that allows you doing in that way. So maybe many other robots also they do allow. So dial gauge can be used. So dial gauge, there is a special arrangement which is here that you see. So it is nothing but a plug. You remove that plug and put the dial gauge over there. Okay, so internally it is arranged this way. The dial gauge looks like this. It has a probe somewhere at the bottom over here. So that is actually a spring loaded thing. Okay, so this is your spring loaded pin. Okay, so that is the gauge pin which you can see here. So that gauge pin basically you see there is a platform over here. That platform is something like this. Okay, this is a notch. Okay, so your pin gets inserted here. Okay, so then it shows the lowermost position. If it is landing somewhere over here, it is little higher up. If it is here, it is higher up. So when it sees the lowermost position, your pin sees the lowermost position. So you can understand by looking at the dial gauge. So it is on the platform, and all of a sudden it will give you a jerk. Okay, goes very much deeper into the notch, and then you see a significant lowest value, and then it comes back to the platform. Okay, so while rotating the joint, okay, it slides over the platform, and finally it gets into this pocket, and then it again comes back to the platform. Okay, so the lowermost value while rotating, when you get, you just record that and save it as a joint angular position, okay, or encoder value. So that is your offset. Okay, that gives you exact 0 position. And there are physical markers also, you see. This also will let you know that you are at 0, 0 position. Okay, so physical markers are for manual recording, and if you are having a dial gauge, that gives you a better picture of it. These are all manual process. You have to jog it manually. So the process goes like the load is mounted. Okay, the robot is to be mounted with the load for which you want to master it. Okay, and the axis is put onto the pre-master position. So you have to locate your robot somewhere on the platform. Okay, if you are sliding, you have to slide on this. You cannot slide if it is too much off. Okay, so you have to be on the platform. That is the pre-mastering position. So when you rotate, it simply can slide and get into the notch. Okay, so that is the pre-mastering position. So load it and take it to pre-mastering position, then put the dial gauge. Okay, and then dial gauge is mounted after removing the protective cap. So it is now fitted with a cap. So that cap is to be taken out, and then you can put your dial gauge there. Okay, the axis position is recorded while the dial gauge shows the lowest position during the slow clockwise or counterclockwise motion. You have to move it very, very slow. Otherwise unnecessary vibrations will come and it will be difficult to actually understand which one was the lowest one. You cannot keep on going back forth like that. Let me just move myself off for a moment. So now this is the dial gauge based mastering technique. Second one is a electronic measuring device, again offered by KUKA industrial robots. Okay, so what it does is, on the same pocket, instead of putting the dial gauge, you also can put this electronic measuring device. It comes in a pack like this with various attachments. So this is the EMD device. Okay, electronic measuring device. So from here it is put here. You have a screwdriver kind of thing that allows you using it like a screwdriver to open the plug which was there. There is a dedicated screwdriver also. This is a simple transducer maybe. So that actually connects the electronic measuring device to this, and finally you have a long cable that actually finally goes to the robot. Okay, this is the smaller micro version of that. So this is the standard one, this is the micro one. So this is how it comes in a pack and it can be used. So the robot is set to pre-master position again because it uses the same notch which is there. Okay, now this time your standard tool has got that pin. Okay, so which gets into the hole, and electronically with the electronic feedback your robot understands, yes, you are at the minimum, you are into this notch now. Okay, that is the lowermost height that you can get. Okay, it is fully automated mastering procedure. So let me just quickly show you one such video. So you see this is the plug which is taken off now, and standard EMD is now put over there. You can see the notch clearly here. Okay, so okay, now you will put that wire here. So you see now robot is now automatically, once the process is initialized, it is gradually moving the link and it gets into the hole, into the notch. Okay, now you can take it out. So it is quite faster procedure. Okay, now put back the cap, and now EMD can be put to the next axis. So one by one you can keep putting this. See now opposite side of the device is used as a screwdriver now. So you see, you can now see the other axis getting opened up. So you can just remove the plug, put the device, again put the wire. So thanks for this video which is there on YouTube. I have given you the full video link here so that you can follow it well. Okay, so hope you got it how this works. Okay, so let us move ahead now. The controller does the slow jogging and automatically detects the best notch position. Okay, it is no more manual, it is fully automatic. So the procedure is very precise and it is faster also. It reduces the downtime. You know, when you have to master after maybe some running hour for different robots it is, so you have to remaster it. So that kills the time of the assembly line or any production unit. So that downtime is now reduced if you are using such kind of tools. So same tool can be used to configure multiple robots, to calibrate multiple robots. So it is not a robot specific most of the time. Okay, so there is a micro version also, there is a standard version also that fits into the different locations for different robots. So manufacturing quality is ensured by frequent calibration. You have to, I told you, you have to keep on doing mastering quite often. Okay, so that way you can maintain the quality of work which is done by this robot. Okay, this toolkit, as I told, it is consisting of standard and the micro EMD device, that is the cable and screwdrivers, those things are there. Again, it supports mastering the external axis also. You can use the same tool to do some external axis mastering also, provided you can create a similar kind of notch there also. Mastering by reference is another very good technique. Let us say you don't have a dial gauge which can go to that pocket. You don't even have your EMD device kind of thing, electronic measuring device. So this is suitable for maintenance work on a mastered robot. Let us say your robot is already mastered. Okay, this is a good robot. Now you want to remaster it. So you must be wondering why it needs to be remastered. It may be simply a preventive mastering that you want to do. Okay, so what you can do, so I'll just make you understand few important terminologies before to that. So the robot is now moved to a reference pose before the maintenance work. So instead of being anywhere in the workspace, now the robot is taken to a standard pose, okay, position and orientation. You can take it to a standard pose before the maintenance work. What is this standard pose? So reference pose or a variable which is there in the controller. What is that? It is an offset between the mechanical zero. That includes the mastering notch. So mechanical zero, you know, it is the notch position, or it is 00, which is marked on the links. All the relative links, you can find them. So they are there in the Canon position. So robot is normally like this, as it is shown. This position is known as a Canon position. This is the mechanical zero position, and the mathematical zero, it is mathematical zero. It is fully extended position when it has mathematical zero. So from this to this, that is the reference which is saved in this variable. So if this is 000, it may be minus 90, and then you go to plus 90, and rest everything is 000. Okay, so this becomes your reference pose. So your reference pose stores a value between 0 to 180 degree or something like that. Okay, so in most of the cases, so if from here to here it is quickly visible, it is 0, 0, minus 90, plus 90, 0, 0, 0. So like that, so that variable will be stored here. So you have to take your robot to this position before the maintenance work. Okay, so you got it. So reference variable may be the default home position of the robot, but not always necessary. Okay, so once you have done the maintenance, so now you keep this robot here, do take out the motor, put back the new one. Okay, and whatever the angle which it shows now, you know, it should be 90 degree, or whatever angle which is at which this robot is now. So you just make your angle. If it shows, let's say 45 degree, but I am at 90 degree, I know. So that 45 degree offset is now saved to the controller. So after the manual maintenance or whatever maintenance work is done, the access value of this system variable are reassigned by the reference variables. So reference variables that was saved earlier before the maintenance now put back to the joints. Okay, so you got it. So you don't need to move the robot in between. Robot should not be moved in between. If at all it moves, everything is gone. Okay, so the state of the robot is then the same as before the loss of mastering. So loss of mastering happened when you remove the motor or actuator or transmission system, whatever. So the position of the robot was not changed during the maintenance work. This you have to ensure. The torque values are retained. In this case, all the torque values, let's say you have programmed for doing some pick and place task using PTP, point to point learning. Okay, so all those values are retained. So all the programs can run as it is even after doing the maintenance job if it is done by reference mastering. Okay, no dial gauge or electronic measuring tool is required for this, and this procedure is also independent of any load variation. Okay, so it is independent of load. So this type of mastering is very, very simple. But again, you must be wondering why we should go for, let's say, EMD tool or any kind of dial gauge kind of mastering tool. So yes, if at all you have bought your system new, then you have to stick to those methods still. Okay, and maybe if you had a breakdown in between due to collision, you cannot go for this method. This can only be applied if it is a planned maintenance. Got it? So still those are still valuable. Those methods are still valuable. Okay, so this method also supports any external access mastering also. Okay, Okay, that's all for mastering and putting your robot to use. So in the next lecture, I'll be discussing calibration of industrial robots. So we'll be using tool center point calibration that I'll be covering in my next lecture using 4-point method and external reference method. Okay, that's all. Thanks a lot.